I'm going to talk about vanishing and exploding gradients. If I have a neural network here, I have these inputs and I have two hidden layers, and then I have, for example, two outputs. I'm going to connect all of these. I have this neural network that has two hidden layers. I send few inputs in, it goes through the network, and then after that it gives me an output, and I'm going to say, for example, the predicted output is going to be 3 here, okay? And then my loss, I'm going to say the actual output, the actual data point. When I give this input, I knew I have to get 5, but I got 3, right? So 5 is the actual answer. And then the loss here is 2, okay? I'm not going to use 2 to go and update the weight in a way that I would get 2, because 2 is just one data point. That data point could have noise. It doesn't necessarily represent all of the other data points. Or even if it's a batch, you don't want to exactly match it to a number. If you're flipping a coin, and if you're flipping a fair coin, and then one time it came tail, it doesn't mean that you're not going to update all of your network to tail. And then next time when you're getting head, you're going to update it to head, because that way you just keep going back and forth, head, tail, head, tail. So you cannot update your data, you cannot update your whole network based on what one data point or one batch of data. But you are traveling toward, you want to travel toward a path that has the minimum error. You're on top of a mountain and you want to go down, okay? But it is so foggy and you cannot see anything. The only option that you have is just to sense with your foot in which direction you have to move, so you're actually moving toward the ground. And you probably don't want to go toward the direction that goes up. So that way, when we explain that, when we are going through the network multiple times, when you're taking each one of these steps, you will feel that it's going to be something like this, right? So you can be at any point of these areas here. And this is going to be, this is called the loss function, okay? In order to be able to use this loss function and not use any specific value of the data point, you have to, we are using partial derivative. So partial derivative tells me, for example, if I am at this point, here, the slope is like this, okay? So the slope is, it is very steep. So I know which direction, if I want to go down, I know which direction I have to go, okay? But then if I am somewhere like here, the steepness is more like flat. So the learning happens less here because you're almost there. You're getting to a minimum. You're getting to a minimum here. Okay, so the gradient, what I'm trying to get at here is that the gradient is the way to go. We're not using subtraction or addition in order to fix the difference, fix the mistake that we made here. We're not using that. We are using gradient in order to get to a place that has the least amount of error. And then, so this is one of the things to keep in mind when we are updating our weights. This is not the only thing, this is not the only gradient that we consider. There is another gradient that we consider, and that is called activation function gradient. So like, for example, if you're having an activation function, because you know each one of these neurons have an activation. For example, I use sigmoid activation function. Sigmoid is sigmoid activation functions looks something like this. First of all, what output do I want this neuron to give me? And that goes to the derivative of loss function, or the gradient of loss. And then also beside the loss gradient and the activation gradient, because both of these are important. One of them is checking for the sensitivity of that neuron, and the other one is checking how much the output should change, how much the output of that neuron should change in order to make the loss to the minimum as possible, or make the least amount of mistake. And then we are using both how sensitive the neuron is by checking the gradients of its activation function And also we're using the loss function, the loss gradient, in order to figure out in which direction we want to go and how do we want to change the output of that neuron. So how sensitive the neuron is and how much the output should change. Both of these are going to be multiplied together. There is another thing that is used, which is learning rate. So you want to see how fast or slow you're learning, and the reason for that is you don't want to something like, for example, if you have a big learning rate, you're here, and then your learning rate is big. You say, okay, you have to go toward down, but I'm gonna go jump, and I'm suddenly gonna end up here because my learning rate is too large. So I'm gonna pass all of these minimums. And jump on the other maximum. I'm like, oh, what happened? Now I have to go back, and then you go back and you jump back and forth like this. It's not going to be good. But if you have a smaller learning rate, then you can, for example, jump from here to here, or jump from here to here and find a minimum. So these three things are very important. Let's talk about them one more time. Loss gradient is important to figure out what output we want our neuron to give. The activation function of the neuron gradient is important because we want to know how sensitive that neuron is. And it shows us how should we change the weight accordingly. And then the other one is the learning rate that we talked about here. So now, what about the vanishing and exploding gradients? What is the vanishing and exploding gradients? So vanishing and exploding gradients is not related to loss function at all. Okay, so loss function is not contributing to that. Exploding and vanishing gradients are coming from the activation gradient, okay, from how sensitive that neuron is. So we talked about the chain rule when we were talking about the back propagation. That means you have to go step by step backward when you are updating your weights. But when you're going step by step backwards, since all of these neurons are connected to each other, like for example, if you're baking a cake, you first have your ingredients. One layer is your ingredients, and then you're mixing these ingredients to get together. You get the batter, that's another layer, and then your batter is going to go to the next layer, which is going to be, like for example, frosting and decorating, and then you have your final cake. In order, if for example your cake ends up being salty and it doesn't taste exactly like the cake that is supposed to taste, that is supposed to have, it's not only be from the last. It can be from the last step, or it can be from the first step, right? It can come from anywhere. But since all of these points are connected to each other, you're gonna have to multiply them together because these are all dependent steps to each other. So you multiply, and then when you multiply, something very interesting here happens. The activation gradient is going to multiply. So for example, if my activation gradient is 0.1, okay, and I have multiple layers, I have so many layers of neurons, and I keep going backward and multiplying 0.1, 0.1, 0.1, 0.1, going to almost become very close to 0. So that means that you're changing that weight by almost nothing. So when you're changing the weight by almost nothing, that means no learning is happening because you're not updating the weights. So that is called vanishing gradient, and it happens for example, it happens based on the activation function that you choose. So for example, if you're using sigmoid, and as you can see here, the gradients are very steep, so the learning happens quite frequently. But when you're getting somewhere close to, for example, 0 or 1, the gradient or the derivative is not steep anymore. It's become more flat. So, okay, that's very off. It's become more flat, so the learning doesn't, so the gradient is going to be very small, and that's going to happen. So sigmoid and 10H is going to be one of the main contributors to vanishing gradients. And then another one that we have is exploding gradients. Exploding gradients is exactly the opposite of this. So you have a very deep neural network, you have multiple layers, and your gradient is greater than 1. So for example, we say 2, and then the 2 is getting multiplied, and over so many layers that you go forward, over so many layers that you go, then it's going to become something like 400 or something. So that is the exploding gradient, which is not good. So both of these extremes are not good, and they can, and the exploding gradients generally happens when you have multiple layers of neurons, or you have, or the weights are not set properly. They're very obviously disturbing the learning. But keep in mind, so vanishing gradient is different from when you're converging, because when you're converging, the learning rate becomes very slow. There's not that much learning happening because your loss is small. Okay, when your loss is small, that means that your network is making less mistake. That means that you're at the point that you don't need to learn anymore. You already learned so much and you can converge. But when you have vanishing gradients, you're still making huge mistakes. You can see that the output is different from what you're supposed to get, but there's no learning happening because of the vanishing gradient, because activation gradient is stopping you from learning, not loss gradient.